Today we're talking about scientific notation and the significant figures. So first off are the significant figures. So significant figures show you the precision of the presented data. So if I said I had a party and about 100 people came, that could mean 75. That could mean 112. We wouldn't know, right? Because we don't know exactly how close to that 100 I actually mean that I am. But if I say 93 people came, you would know exactly how many people were there, right? So that's what significant figures does. It tells us how exact are we being in this presentation of the data. That's why it's important. So let's figure out how to do it. Our first rule, so you're going to want to write down these rules because we're going to use them over and over again. So get out your notebook, probably put a title, something like significant figures and scientific notation. Don't forget to put that in your table of contents like we always do. So the first rule is that non-zero digits are always significant. So if you have anything from ones to nines, they're always significant. So in that number, 123,456,789, it has 9 significant figures because there are no zeros in there. All of them are significant. Our next rule is that leading zeros, zeros that come before the first non-zero number, are not significant. So anything that comes before the first non-zero number don't count as significant figures. So if you look at that problem or that number there, you will see 0.00001230040 or 45. You only start counting at the first non-zero number, which is your 2. So our numbers are 1, 2, 3, 0, 0, 4, 5. So we have 7 significant figures. Or they can also be called significant digits. It depends on what you read. It's the same thing. After that are what you call captured zeros, some people call it that, or zeros between 2 significant figures. Those are always significant. So if you look back at that last one, I said that the 2 zeros between the 1, 2, 3 and the 4, 5 count as significant. That's because captured zeros are significant. So in the number 1.023, that 0, because it comes between the 1 and the 2, is significant. So that number has 4 significant figures. Trailing zeros. So we had leading zeros. Now we have trailing zeros, the ones at the end. Trailing zeros are significant if they're to the right of the decimal and after a non-zero number. So if we go back a couple, here we had zeros after the decimal point, but they were before the first non-zero number, so it wasn't significant. But trailing zeros, any zeros that come after our non-zero numbers, are significant if they happen after the decimal point. So in the number 123.450, that 0, because it's to the right of significant figures and it's to the right of the decimal point, then it's significant. So that number, 123.450, has 6 significant figures. So now it's time to practice. So I'm going to write down some numbers and you're going to tell me if they're significant or not. If I have the number 0.00520, how many significant figures are there? So look at your rules that we wrote down and tell me how many of those are significant.
5? Or am I doing that wrong?
Okay, let's talk about it. So what is our first rule?
Numbers 1 through 9 are significant.
Okay, so we know for sure that this one and this one are. What's the next rule?
Zeros before the first non-zero number are not important.
Right. It's actually significant. That's a specific term. So it's not the same thing as important numbers. Significant figures is a specific term that we use in math and in science. So significant. So these are not, because they come before the first non-zero number. So those don't count. What else do we have? What's the next one?
Zeros between two important figures are important.
Okay, so we don't have any zeros in between our two significant figures, right? And then what's our last rule?
Zeros to the right of the decimal point is important.
Right. So our decimal point's over here, and our 0 is off to the right of it, and this is important, and it's to the right of the first non-zero digit. So these are also, these two right here are also to the right of the decimal point, but they're before the first non-zero digit, so they don't count. But this one counts because it's after the decimal point and it's after the first non-zero digit. So this problem has 3 significant, that's not how you rate that, significant figures, or we can say 3 sig figs for short. Okay, what about this number? Look through your rules and think about what you need to look at to see how many significant figures there are.
2.
Very nice, that's right. So non-zero digits are significant. We don't have any leading zeros. We do have 2 trailing zeros, but they're not after the decimal point. So we only have 2 significant figures in that one. Good job. Now, what if I wrote this? How many significant figures are there?
3.
Okay, that's a good guess. So we have, these are the first 2. So we know those are important, but let's talk through our other rules. So what are our other rules?
Zeros before the first non-zero number are not important.
Right, we don't have any of those.
Zeros between two important figures are important. We don't have any of those, right? And zeros to the right of the decimal point is important.
Right. So zeros to the right of the decimal are important if they come after a significant figure. So that means this one's a significant figure and this one's a significant figure. So go back to the rule before that one. What does it say?
Zeros between two important figures are important.
Right. So since this is a significant figure and this is a significant figure, that means these 2 are now.
Oh, right.
So you gotta kind of go back sometimes. So we actually have 5 significant figures now. What about, I'm gonna do a tricky one, and it's gonna come with, we're actually gonna learn more about it here in a minute when we talk about scientific notation, but I just want you to see what it's gonna look like. So for this one, when you look at it, you ignore this part, okay? So just in this one, how many significant figures are there?
4.
Exactly, because we have 2 non-zero numbers and then we have 2 captured zeros. So that's 4 significant figures. So good job. So then, significant figures in addition and subtraction. There are special rules for when you're adding and subtracting and trying to figure out significant figures. So when you're adding and subtracting, you use the same precision as the least precise measurement. That's nice to say, but we haven't talked about what precision means. So a number is as precise as how many decimal places there are that are significant. What is the last significant figure in 1.2?
2.
2. What's the last significant figure in 3.45?
5.
5. So you have, what place value is the 2? What place is it in?
The forgot how to say it. It's the tens.
Yep, the 2 is in the tenths place. So the first number is precise to the tenths place, is what we say. The second number is precise to the hundredths place. So we're going to use the precision of the least precise. So between those two, 1 to the tenths and 1 to the hundredths, the least precise is the tenths place. So that means our answer can only go to the tenths place. So you add that together and you would say it's 4.65, but we want to round up so that we only have to the tenths place. So it's 4.7. Does that make sense?
Sort of.
Okay, we'll do some practicing and hopefully it will make sense then. All right, so let's try some of these. So if I have 12.04 meters plus 3.0 meters plus 0.123 meters, first of all, we want to add those. So you add them first, and then you decide how many significant figures you need in your answer after. So we say 12.04, 3.0, and 0.123. Then we're going to add those together. We start over here on the right, 3, and then 4 plus 2 is 6, 0 plus 0 plus 1 is 1. We move down our decimal, 2 plus 3 is 5, and then a 1 at the front. So that's our answer, but we can only report it to the same precision as the least precise. So which one of these is the least precise?
3.0.
Right, because it has the fewest numbers after the decimal place. So it only reports to the tenths. So we can only report to the tenths. So our actual answer that we would write down would be 15.2 meters, because we're going to round up here. Then if we have 8.75 grams minus 2.4 grams, we're going to take 8.75 minus 2.4 and subtract. 5 minus 0 is 5. 7 minus 4 is 3. Move down our decimal. 8 minus 2 is 6. And how many decimal places are we going to report to?
The tenth.
Right, because our least precise number only goes to the tenths place. So our answer would be 6.4. And we don't forget our labels. We always want to include our labels. So 6.4 grams. Let's try one more. 7.6 kilograms plus 0.08 kilograms plus 0.5 kilograms. You tell me what I should do.
First, we need to stack them so we can add them.
Okay.
So 7 staying on the top, and then the 0.08 kilograms. I don't know how to say that. And then the 0.5 kilograms. Are those kilograms? Yeah, those are kilograms.
Mm-hmm.
And then we add like normal. So it's 8, 11. And then we figure out which has the least precision, but there's 2. So how do we figure that out?
Yeah, they're the same. So those are the 2 least precise, so we're just going to go to the tenths place because they're both the tenths place, right? Yes. So what will our answer be?
8.2.
Right. 8.2 kilograms.
Yeah.
Okay, so we've done our adding and subtracting. Now we're going to move on to multiplying. So when you're multiplying and dividing, you use the same number of significant figures as the number with the fewest significant figures. So that sounds like the same thing, but it's not. So our example there is 1.234 times 5.6. When we multiply that, you get, I guess I didn't actually write that up, what your whole thing would be. But you have to round it to 6.9 because the 5.6 has 2 significant figures. The 1.234 has 4 significant figures. So you use the one with the fewest significant figures, okay? And I'll show you in just a second why that's not exactly the same. So we're going to practice using significant figures in multiplication and division. If we multiply 2.50 times 3.2, we would do it normally. 2.50 times 3.2. 2 times 0 is 0. 2 times 5 is 10. Carry the 1. 2 times 2 is 4 plus 1 is 5. Then we move over 1. 3 times 0 is 0. 3 times 5 is 15. Carry the 1. 3 times 2 is 6 plus 1 is 7. Then we add. 0 plus 0 is 0. 0 plus 0 is 0. 5 plus 5 is 10. Carry the 1. We've got 8. And then we have 1, 2, 3 numbers after decimals. So we go 1, 2, 3. So our answer is 8.000. But which one has the fewest significant figures?
3.2.
Right. That has the fewest significant figures. How many does it have?
2.
2. So we could only report to the 8.0. And so at this point, it looks... Yes, but we need the precision to say it's exactly 8. It's not 8.4. It's not 7.8. It's 8.0. So that tells us it's actually exactly that amount to the nearest tenth. Okay? Now, so far, we're still looking like it's the same for addition and subtraction. But this next one will show us that it's not the same. If I do 5.0 times 2.1 times 10, we do 5.0 times 2.1. You have 1 times 0 is 0, 1 times 5 is 5. Move over 1. 2 times 0 is 0, 2 times 5 is 10. Gives you 0, 5, 0, 1. And then we have 2 decimal places. We're going to move over twice. That gives us 10.50. Then we're going to multiply by 10. And we do that by moving our decimal point over. So we have 105.0. So if we were going to do it by the addition and subtraction, we would say our least precise has no decimal places, so 105 is the answer. But what is our rule for multiplication and division? You use the same number of significant figures as the one with the fewest significant figures. So what we have to do is figure out how many significant figures there are. So here, how many significant figures are there?
1.
There are 2, because our 0 comes after the decimal point and it's after the first non-zero number. So there are 2 significant figures here. What about here?
2.
There are 2. What about here?
1.
There's only 1. So we can only use one significant figure, which means that we can only write it with one significant figure. So that means we actually have to round all the way up to the nearest 100. So we would have to report our answer as 100. Because if we had this, let's say this was an 11 instead, we could report it to 2 and be 110, but no, we only have one significant figure, so we have to go all the way up to 100, because then that has one significant figure and it matches this one. Let's do a division one. So if we divide 75.6 by 2.4, how do you actually write that down? 75.6 divided by 2.4. You can write it like this, but you can't divide something with a decimal in the divisor. So what do? To do that, you move the decimal point over for the divisor and the dividend both the same number of times. So we move it over once, which means we move over the dividend once. So it'll be 24 and 756. Then we do our division. How many times can 24 go into 75?
Can I look on a calculator?
I guess so, but think about quarters. How many quarters are in 75 cents?
3.
3. And 24 is pretty close to a quarter, right? It's pretty close to 25. So we're going to try 3. So then we'll do 3 times 4 is 12. Carry the 1. 3 times 2 is 6 plus 1 is 7. Then we subtract. 75 minus 72 is 3. We bring down our 6. So 24 goes into 36 only once. So 6 minus 4 is 2, and 3 minus 2 is 1. But we want something more precise, so we bring down 0. 24 can go into 120. I'm going to say 4 times. We do have to put a decimal point once we add the 0, right? So 4 times 4 is 16, carry the 1. 4 times 2 is 8, plus 1 is 9. Oh, I think you might have been right.
It's 5.
Yep, you're right. It's 5. So we got to go back. So it does go 5 times. 5 times 4 is 20, carry the 2. 5 times 2 is 10, plus 2 is 12. So it's actually a nice round number. Our original numbers were here, 75.6 divided by 2.4. So which one has the fewest number of significant figures?
2.4.
2.4, which has 2 significant figures. And so how can we report our answer?
We round it.
Right. We have to round this to have 2 significant figures. So our actual answer will be 32. Because, again, if we were doing addition and subtraction, we would go to 31.5 because the least precise has a number in the 10th place. But with multiplication and division, you go to the same number of significant figures as the one with the least significant figures. So we're moving on from significant figures to scientific notation. So scientific notation communicates how many significant figures there are, so they are related, especially when there are significant zeros. So you were asking about, wouldn't 80.0 be the same as 80? And I talked about, yes and no, it's pretty close, but we need to know that there's exactly 80.0, not 80.2 or 9.5 or whatever. We need to know that it's exactly 80.0. But if you have that number, sometimes it's hard to tell. If I had a number like 1,234,560, is that last zero significant or not? We don't know. We don't know because it's hard to know how people are reporting it. So this is a way to say, you know what, that last zero, usually we would say no, right? Because it's a last zero that comes before the decimal point, so it's not significant. Usually we would say that. But if it is significant, we could write it in scientific notation, and that would let us know, I do need to count that zero. It is that precise. So let's look at an example. If you have 6.20 times 10 to the third, that tells me you have 3 significant figures. If we just move that out, so times 10 to the third means we move the decimal point over 3 times. So that number would be 6,200. If we were just going to look at that based on our rules of significant figures, that would mean we only had 2 significant figures, right? Only the 6 and the 2, because the 2 zeros following, because there's no decimal point, and then another 0 after or something like that, we would only have 2 significant figures. But we want to show that 6, 2, and the 0 are all significant. So we write it that way, and that actually tells us we have 3 significant figures. Then scientific notation rules. You put only one non-zero digit before the decimal point. So before the decimal, you can only have 1 digit. Then you have the decimal, then you have as many after that as you need. And only significant figures go before the multiplication sign. Otherwise, that 6.20, we still wouldn't know if the 0 was significant or not, right? If we didn't know that you can only write down significant figures. So we're going to practice using scientific notation. So if I have the number 450,000, how would I write that in scientific notation? What's our first rule?
Well, I think first we gotta figure out how many significant figures there are.
We have to figure out how many significant figures there are. So what are the significant figures?
4, 5, and that's it?
That's it. So our 4 and 5 are our only 2 significant figures. So that's all that can go before the multiplication sign. And then So that's going to be what we have. But our first rule is that only one number can go before the decimal point, right? So our decimal point is going to go here. So it's going to be 4.5 times 10 to the something. And how do we figure out what the something is?
How many times we had to move the decimal point from where it originally was?
Exactly. So we start here and go over 1, 2, 3, 4, 5. So 4.5 times 10 to the 5th would be how we write that in scientific notation. What about instead if we have 0.000072? We're going to write that in scientific notation.
We figure out which ones are the significant figures.
And what would those be?
7, 2. Is that it, or the zeros?
That's all, because the leading zeros, any zeros that come before the first non-zero digit are not significant. So just the 7 and a 2.
Okay, and then there can only be one significant figure before the decimal point, so we put it in between the 7 and the 2. Those go before the multiplication sign.
Yep.
And then for the
Exponent.
yes, the exponent, we have to figure out how many times we move the decimal point, but we're going in to the right, so it's gonna be a negative.
Exactly. Exactly. So we're going over 1, 2, 3, 4, 5, but we're moving to the right instead of the left, so it's negative. Then if we have the number 6.02 times 10 to the 23rd, this is a number you're going to get very, very familiar with because this is what we call Avogadro's number, and it's important in chemistry. So 6.02 times 10 to the 23rd. If we were going to write that in regular form, in standard form, how we usually write it, what number would that be? How do we figure that out?
We move the decimal point.
Which way?
We move it to the right.
Right. So I said to the right, we moved it here. That's if you're going from standard form to scientific notation. So it's easier to think about it as if you have a negative exponent, that means it's a really small number. If you have a positive exponent, that means it's going to be a big number. So we have a big number. So we're going to go to the right since we're going from scientific notation to standard form. And we're going to write a really big number. We're going to move the decimal point 23 times. We move it over that many times and fill in each of our little loops with zeros. And I'm writing over my other writing, which is not ideal. So we actually end up with
a big number.
A huge number. That number. So I guess it would be 602 sextillion. Let's do one more. We're going to say 5.00 times 10 to the negative 3 and write that in standard form.
In order to do that, we got to move the decimal point 3 times to the left. Because it's going to be a small number.
So we add our zeros and we put our decimal. So 0.00500. And then we know, because it was 5.00 times 10 to the negative 3rd, we know we have 3 significant figures. So we have to keep these 3 significant figures. So we have to write it like that, not change it to this, right? Because we got to keep those 3 significant figures. So I want you to make sure that you have written down all of the important things. These are things that you're going to need to use over and over and over and over in chemistry.